formation enthalpies are going to be the final application of enthalpy as a state function. So the enthalpy of formation is the enthalpy change of forming 1 mole of a substance from its elements in their standard states at ambient pressures. Okay, so that's a pretty big mouthful. But if we think about enthalpy of formation, basically what we want to think about is if we want to take any substance and think about what is the enthalpy change of the reaction forming that substance from elements. So if we started with elements and then basically they combined to give that substance, what would be the enthalpy change for that reaction? So we got an example of carbon dioxide. We'll parse this out. We can see the substance of interest is the product. In this reaction, it is the only product, and the coefficient is always 1 on this. So we still do need balancing, but this is, again, we're kind of going to play, our rules for coefficients are going to be a little bit different than we've seen kind of in general, that the coefficient, we have 1 product and its coefficient is 1. So then the reactants are all the elements in their standard state. So carbon dioxide has 2 types of elements, carbon and oxygen, and then they are just basically in their elemental states. Oxygen's a diatomic, so it's O2 molecules, that's its standard state, and carbon is not a diatomic, so it just gets carbon. But it does have GR, which stands for graphite. You'll also note there's delta HF naught, that degree symbol is naught, that's NaUGHT. So that means that you are at standard pressure, which just means the pressure of the air. Delta HF values, these enthalpy of formation, you will note that F stands for formation. Those are at a specific temperature. So you do need to say what temperature you're forming this substance at. You're under basically air pressure conditions, but you do need to specify that information. So this delta HF naught, the change of an enthalpy of forming, where the F comes from, and a given substance from elements at their standard states. So it is worth pointing out a little bit about this standard state. We're not going to go too much into it, but the standard states of the elements a lot of times are given from the periodic table, right? Remember we talked about that the color of the font of the symbols can really denote, is it a solid, is it a liquid, is it a gas? Most of the metals are solids except for mercury. There's the diatomics, so we need to remember those, what their phases are. Carbon, you saw in the last one, carbon is a little bit tricky. So carbon is a solid. If you looked on the periodic table, it would have the color solid. But there's 2 common types of carbon. These are called allotropes of carbon. They're different forms of solid carbon. One is graphite, so like common pencil lead, and one is diamond. Those are both pure carbon that have different stabilities under different conditions. Under ambient conditions, i.e. out in the atmosphere, graphite carbon is more stable. So diamond doesn't fall apart, it's just not the preferred form. This is why if you form like pure carbon, it doesn't form diamond under, in say, the open air. You need to go like to the middle of the earth to form diamonds. All right, so these formation enthalpy values are just tabulated. So this is a table from a different book that I've used where you're just looking at a bunch of, you can see the chemical formula, and then right next to it is the delta HF formation. So a bunch of people have just done these experiments to figure out what is the enthalpy change associated with forming 1 mole of N2O4, of carbon monoxide, of hydrogen fluoride, of copper 2 sulfate, whatever it is, you can have those tabulated values. Sapling has a table of this. This is the sapling table. You will note delta HF is what you want. You will note, again, these are specified as being at a temperature. 298 K is a temperature unit that we'll talk about later. This is just room temperature, basically. 25 degrees Celsius, kind of comfortable conditions, lab weather. There are these other 2 tables, delta G, F naught, you can see a different type of formation, and S naught, no delta on that one. These are other thermodynamic properties. If you come back for 1412, you will learn all about those, and you can do problems where you use all columns in this table. But you'll note, I forgot to point out, they're alphabetical roughly by symbol. So silver's at the top, and you can see this is huge on sapling. It's only made it to B for boron. It goes all the way down. There are a ton of compounds that are in that table on sapling. One kind of quirky note, when we're looking at forming these elements, based on the rules of how we define formation enthalpies, elements have 0 formation enthalpy because you go from element to element in the formation reaction. It's not very exciting. And so these delta HFs for elements are always going to be 0. What that kind of is going to give us is a benchmark or kind of a baseline that those are 0. We can compare everything else to those values. And so the idea of comparing to those values is we could imagine, say we look at 2 different substances. So I have ethanol here and I have dimethyl ether. And both of these molecules have 2 carbon atoms, 1 oxygen atom, and 6 hydrogen atoms. So they have the same number of atoms, they're just arranged in different ways. And they have different enthalpies of formation. And so those enthalpies of formation, right, are all tied to whatever the standard elemental states are. So 2 carbon atoms, 3 hydrogen molecules, and a half an oxygen molecule. Okay, and so they all come from that kind of standard, there's that same baseline that they come from. And then their enthalpies of formation then correspond to the different distance from that single baseline down to here. So what we can do is if we want to know the delta H of going between these 2 things, say from dimethyl ether to ethanol, how we can imagine it is, ideally we would do it in a single step where we do this, right down from dimethyl ether to ethanol. But instead, because enthalpy is a state function, we can envision it as instead, let's go to the elements, basically take dimethyl ether, break the molecule apart into its elements, then take those same elements and combine them into ethanol. And if we know the delta H for that kind of roundabout process, that would be the same as the delta H for the direct process. And this idea, take all of the reactants, turn them into their atoms or elements, then form the products, comes together in this equation right here. Delta H of the reaction is equal to the sum over products of the formation enthalpies of those products minus the sum over reactants of the formation enthalpies of the reactants. So this is why we have all those tabulated values. Basically, for any chemical reaction, we can figure out what the delta H is for that reaction based off knowing the tabulated enthalpies of formation for all of the component substances. This is using Hess's law. Basically, you're cooking Hess's law into this equation, but we can avoid having to figure out the Hess's law for ourselves. Let's look at an application. What is the change in enthalpy associated with the following reaction? I have 2HCl plus F2 becomes Cl2 plus 2HF. What do we want? I want the enthalpy of a reaction. Okay, this prompt is pretty bare. It just asks what is the delta. This is basically, you could also just say what is delta H? What is the change in the enthalpy? 2H for my reaction, 2HCl plus F2, Cl2, 2HF. Okay, what other information do I have? I just have a reaction. All I've got is the reaction. There's no calorimetry information. We've seen that before. There's no Hess's law. There's no reference reactions. All I have is this reaction. And when all you have is a balanced chemical reaction, that's where you need to use your formation enthalpies. That's the only thing that you can use. Those enthalpies of formation, those tables are going to come to your aid. So let's see how we use them. All right, we want an enthalpy change. Right, we want delta H for this reaction, and we are given no other information. We have nothing about reference reactions. We have nothing about heat. Right? We didn't heat up some water or anything. We have to use formation enthalpies. We have to use tabulated enthalpies of formation in order to make this work, in order to do this calculation. So whenever we're given just an equation like this, delta H, it's just a chemical equation, we know we can turn to the sum over products delta HF naught, minus a sum over reactants, delta HF. Okay, so let's take a look at what that looks like, a sum over products. Well, my products are chlorine and 2HF, so it's going to be delta HF naught of the chlorine plus 2, which comes from that coefficient, times delta HF naught of HF. Different HFs, I want to be careful. So this 2 shows up right there. Okay, we keep those 2's, any coefficients show up because this delta HF would be for like 1 molecule, 1 mole, and we're reacting 2 moles. So that's the products. We subtract from that, adding together all of the reactants. So that is 2 times delta HF naught HCl. Again, I keep the coefficient, plus delta HF naught F2. And so again, that 2 becomes that 2. And you'll note there's 1s, right? There's like a 1 in there, and you don't write the 1 in both of those contexts. So in order to get that, we want to use our tabulated information. This is just one that comes from a different chemistry book, a different textbook. You can use this. You can go to Sapling, has a huge table. The book has a table. There's all sorts of information in there, but you just find them. And so if we do that, so Cl2 is our first one. And so we can find Cl2 is 0. That's because it's an element. Remember, elements in their standard state have 0 enthalpy of formation, times 2 times HF. The HF value is negative 271.6 kilojoules per mole, square brackets, minus 2 times the HCl. That's negative 92.3 kilojoules per mole. And because fluorine is again elemental, that one is 0. And so you want to be careful. There's a lot of signs. It's very easy to make mistakes with the signs here. Basically, you want to think all of these want to be added together. Some of those are negative numbers. All of these want to be added together. Some of them are negative numbers. And so you add up all these together, and then the whole answer gets subtracted from this whole answer. So I'd recommend doing this in multiple steps and explicitly writing them out, because this is 0. 2 times negative 271 is negative 543.2 kilojoules per mole minus negative 184.6 kilojoules per mole. So this corresponds to this first, the product right there, and then the reactant. So you add up all those and then you subtract. It's very easy to only apply the negative to the number and forget to apply it to the back. So I would recommend adding all of those up and then using that. So 543.2 minus negative 184.6 gives me a total reaction of negative 358.6 kilojoules per mole. So that's the delta H for the whole reaction. And this is really the holy grail now. We did nothing. We have done 0 experiments. We haven't even had to do any difficult Hess's law or kind of tedious Hess's law. We just use the equation, use tabulated data, thanks to all those people who did the experiments to figure out that data. Plug them in, and then now we have our answer for the reaction. It's the same output. It gives us information about the reaction before we do it. We didn't have to do any experiments to obtain this number. We can also see one value with this is it kind of parses out some information or kind of why this is the value. When we're looking at what this really is showing is that this delta H is basically forming the products minus forming the reactants. So how you can think about what this model of reaction is, you take these reactants, you break them apart into their elements, then you combine those elements into the products. So You get the energy of forming all the products, hence the positive, there's no negative in front of that. You lose the energy of forming the reactants because you have to break them apart. You unform them. And so we can see that overall this reaction is exothermic. It's negative 358.6. That is because you gain a lot of energy from forming these reactants, namely HF, and you don't lose that much energy from breaking apart the reactants, right? You make a lot of energy from the products, you don't lose that much energy from the reactants. So negative 543.2 is your basically how much energy is released from forming just HF. HF is a very stable compound, and it doesn't cost a lot to break this HCl. So you break apart, you unform the HCl, and then you form the HF, and that's really stable. That releases a lot of energy to form this HF. So we can get not only an answer as to like what the delta H for the reaction is, but a little bit insight into why. HCl, not a very stable compound, or relatively not super stable. HF is very, very stable, and so that's why you release all of that energy. Participation 618, question 2. What is the change in enthalpy associated with the following process? H2OL becomes H2OG. This is the second question on participation 618, due Thursday, June 18th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, what is the change in enthalpy associated with the following reaction? H2O liquid becomes H2O gas. There's some useful information in the additional resources folder that might be handy in answering this question. Okay, that was another question on participation 618. Our participation assignment due on Thursday, June 18th. That's halfway through this set. We're almost done with chapter 5, then we'll get into chapter 6 for a little bit. See you in the next video.